going to investigate which of these dyes that we utilize in chemistry has the highest melting point by using the Vernier melting station. The dyes we will be testing in lab are blue number 2, yellow number 5, and red number 40. All these dyes are legal for the use of food coloring. These are the different structures of the dyes that we will be using. Okay, I'll pause it.
This structure right here is blue number 2, here is yellow number 5, and here is red number 4.
The independent variable that we will have to control in this, have the control over in this experiment is the color of the dye. The dependent is the melting points, the temperature that the particular dye melts at, and things we will need to make sure do not become variables are the starting temperature of the dye, the pressure in the room, and the amount we use of the dye. Our hypothesis is that we believe yellow number 5 will have the highest melting point, red number 40 will have the second, and blue number 2 will come in last with the lowest melting point. We believe this because when looking at the structures of the dyes, the yellow number 5 has the most bonds in general, break, and the most double bonds. If you look at the intermolecular forces, it has 3 points at which it has an ionic bond, which is the strongest of the intermolecular forces.
Alright, so since yesterday the Vernier melting station didn't work, we're having to melt it over a Bunsen burner. And right now we're doing blue 2. Yeah, the temperature, you can see, is already way higher than it was yesterday. And
there's the thermocouple. We're using the thermocouple to take the temperature instead of the melting station because it can read the temperature a lot hotter. And let's show the graph. As you can see, the graph looks a lot different than yesterday.
As you can see, it's starting to melt, and it's bubbling actually a little bit. I don't know if you can really tell. And the temperature it's at is 300 is at, give it a second, still going up.
Temperature is at around 850 degrees Celsius to 700.
As you can see, the temperature is around 930 degrees Celsius to up to 960 degrees Celsius it's gotten up to. And that's where the temperature is melted at about.
It is now finished melting. Just like that.
Alright, this is an image of our data table. It's showing the temperature that each dye melted at and how long it took for each one to melt at in seconds. As you can see, yellow 5 melted at the fastest at 8.3 seconds and at the highest temperature of 1048 degrees Celsius. There was a variable, and that was that we could not control the temperature of the Bunsen burner, and so with yellow 5 being at the temperature, that most likely caused it to melt so much faster.
As you can see from our graph, the Y variable is temperature and the X variable is time. And the dye with the highest melting point was the yellow number 5, and you can see it's the top line. And then the dye with the medium melting point is red 40, it's this line right here. And the dye with the lowest melting point was blue number 2, which is right here. I'm doing this for the love of chemistry.
So in our hypothesis, we believe that yellow number 5 would have the highest melting point, that red number 40 would have the second highest, and blue number 2 would come in the last with the lowest melting point. We believe this because when we were looking at the structure of the dyes, yellow 5 had the most bonds in general to break and the most double bonds. If you look at an intermolecular forces, it has 3 points at which it has an ionic bond, which is the strongest of the intermolecular forces.
So in our lab, we said we were going to be using the Vernier melting station, but it maxed out at 302 degrees Celsius, and our dye still had not yet melted. So we had to move on to using a Bunsen burner and a crucible. And with that, the melting points of all of them were somewhere around 900 degrees Celsius, but it took only for yellow 5 in our hypothesis, we believe that would be the longest lasting one. In fact, that one was the fastest with 8.3 seconds. But this problem was that we could not adjust the temperature on the Bunsen burner to be a specific temperature, and that one was at 1054 degrees Celsius. And with that, that kind of makes there a variable that the temperature we cannot control.
Is the thermocouple is not as accurate as the Vernier melting station that we used, but the Vernier melting station didn't go to a high enough temperature, so we had to use the thermocouple in the long run. And the problem is that it didn't have a constant heat temperature because it was in different parts of the flame at different times. We couldn't really control that because it kept moving. So it would be in the blue part of the flame, which is the hottest part, or the red part of the flame, which is less hot. Some of the ways we can improve this is get better lab equipment, which wouldn't limit our results. So, something that would more accurately measure this, than a thermocouple, and we could have had a constant heat temperature. And we can apply this to the ways we cook food, and like knowing that the yellow 5 has the lowest temperature. If you wanted to cook a higher melting point, like melting higher point temperature of food, then you would not use the yellow 5 because that has the lowest melting point, so it would melt pretty easily. And we learned, what we learned is important because we learned how to utilize new lab equipment and that we've never used, and that you will never melt a dye in the foods if you put it in and you're cooking it, because that was an important argument that we brought up, because you don't want a dye to melt in your food because that'd be disgusting, and it's important that it doesn't because that'd probably be bad for you.
Aha!